In our previous videos, we talked about the thermodynamics and the kinetics of organic reactions in general. And in this video, we're going to focus on energy diagrams, which can be used to describe the progress of a reaction. And we're going to look at how these provide useful information about thermodynamics and kinetics. First of all, let's consider energy diagrams and thermodynamics. Now, if we have a general reaction where we have some reactant R going to form some product P, then we are looking at the reaction progressing as we move along the right, and we're looking at a difference in energy as we're moving up. So I'm using E to be generic about what type of energy. This could be a delta H or it could be a delta G. If we are talking about delta G, then going from reactants at low energy to products at high energy, this because delta G is positive, so this is an endergonic reaction. Or if we're thinking about it in terms of delta H, still the delta H is positive, so we would call this an endothermic reaction. Let's look at a second example where maybe this represents the energy of the reactants, and then this represents the energy of the products. So we're focusing on this energy difference, and if we are looking at delta G, this delta G is negative, so this is an exergonic reaction. Or if this is delta H is still negative, so this is an exothermic reaction. Now it's possible to have a single step reaction that is endergonic or endothermic. It's possible to have a single step reaction that is exergonic or exothermic. But it's also possible that we have multiple steps that make up a single reaction. And it's often very useful to be able to show the multiple steps on the same energy diagram. So let's say that here is the energy of our reactants, and here is the energy of our products. But this is just step one of a two-step reaction. In the second step, the product of step one becomes the reactant of step two, and then the reactant of step two progresses to form a product of step two. Focusing on the delta G or delta H of the first step, this would be endothermic or endergonic, where we have a delta G or delta H is positive for step one. And then this would be step two, where this is the energy difference that we are looking at. So for step one, delta G or delta H is positive. This is an endergonic or endothermic reaction, depending on which one we're talking about. For step two, the delta G or delta H would be negative. But if we consider the energy of the overall reaction, then we want to focus on the overall reactant and the overall product. So not just the reactant product of step one or step two, but the reactant of step one going to the final product of step two. So this is the energy of our reactant, trying to make this a straight line. And then this is the energy difference of the overall reaction. And so overall, we have an exothermic or exergonic reaction. Keep in mind what this tells us. So looking at this reaction over here, going from reactants to products, this is an unfavorable or non-spontaneous reaction. What that means is that at equilibrium, we're going to have more reactants than products. Here we have a favorable or spontaneous reaction, which means at equilibrium, we're going to have more products because these are lower energy, and greater concentration of products, a lower concentration of reactants. For this two-step process, the relative energy here or the relative energy here isn't as important as the relative energy here. And so what we can see in the end is that this is a favorable or spontaneous reaction, and at equilibrium, we will have more products than reactants. Coming back to the sample reaction that we talked about earlier in this chapter, this could be the energy diagram for the reaction of an alkene with HBr. So step 1 involves the alkene reacting with HBr to form the carbocation and Br minus. And then step 2 involves the Br minus recombining with the carbocation to form the alkyl bromide. So I'm only showing this hydrogen because let's pretend that this is the one that just became connected, right? We already have 2 other hydrogens here, 2 other hydrogens here. They're still here, they're just not shown. Now, for this reaction, step 1, here we have a charged species, the carbocation, and the carbon doesn't have an octet. This is very high energy. So this step, it makes sense that this one is endergonic or endothermic. The product is much higher energy than the reactant. And then the blue step, we're going from a high energy intermediate to a product that is neutral and everybody obeys the octet rule. So between the reactant and the product, we're going to much lower energy. One other thing I wanted to highlight here where we have this 2-step reaction, these are our reactants. This is our product. And so what we have here would be the intermediates. And so on the energy diagram, this represents the energy of the products of the first step or the reactants of the second step. So this is the reaction intermediate. Or in this case, we have a pair of intermediates. Next, let's consider a completely different example where we're looking at energy diagrams and kinetics. Let's say this is the energy of our reactant and this is the energy of our product. Right now, I don't care about thermodynamics, so here I'm showing an example where our delta G would be 0. In addition to the reactant and the product, we also have the reaction progress. What is happening for that reactant to change into the product? So what we've been looking at so far in energy diagrams is rather incomplete because there's a lot more to the picture. In between the reactant and the product of any reaction step, we have another important species, the transition state. And if we think about the progress of the reaction, we are going from a reactant at a particular energy. There is an increase in energy as molecules are bumping into each other, bonds are stretching, forming, breaking. We reach a transition state, which is at a maximum energy, and then the energy decreases until we reach the product. So the transition state, or the TS, this is an intermediate structure. So it's somewhere, in terms of structure, it's somewhere between the structure of the reactant and the structure of the product, right? I call it an intermediate structure, but do not confuse that with a reaction intermediate. So the transition state is this really, really short-lived species. We cannot observe it. We can only deduce or infer that it exists, but understanding the transition state is really important because the energy difference between the reactant and the transition state, this is called the activation energy. So EACT is a symbol that I often use. In the book, they use delta G double dagger. So this is if we're specifically focusing on free energy, and the double dagger refers to the transition state. So what we're looking at is the Gibbs free energy difference between the reactant and the transition state. Now, we care about the transition state because we care about the activation energy, because the activation energy determines the rate of the reaction. So notice, up here, we talked about thermodynamics. Thermodynamics gives us information on the relative energies of the reactants and the products, and that gives us information on the concentrations of the reactants versus the products at equilibrium. The kinetics have no impact on the thermodynamics. When we're talking about kinetics, the focus is on the transition state and the activation energy, which determines the rate of the reaction. So the rate of the reaction depends on the reactant and the transition state. It has no impact or no dependence on the relative energies of the reactant compared to the products. So kinetics are independent of thermodynamics. Thermodynamics are independent of kinetics. Now, here we have a few different examples of energy diagrams for different reactions. If we compare, first of all, A and B, looking at the reactant compared to the product, we see that the product is lower energy. So this is the delta G of the overall reaction, and this delta G is negative, which means this is a favorable or spontaneous reaction, which means at equilibrium, we have more products than reactants. Looking at B, once again, reactant to product, the products are lower energy, so our delta G is negative. And this is another favorable or spontaneous reaction where at equilibrium, we're going to have more products than reactants. But the thermodynamics is only part of the picture. We should also take a look at the transition state. So looking at the transition state in A compared to the transition state in B, we have a significant difference. Difference in energy between the reactant and the transition state in reaction A, this is what we care about, right? This energy difference, this is the activation energy. Because the activation energy is small, this reaction is going to be fast. I drew the blue arrow. This is what they represent here with the delta G double dagger. This is the activation energy. In B, going from our reactant to our transition state, the blue arrow again represents the activation energy. So the delta G double dagger, this is the activation energy. So because this reaction has a much larger activation energy than this one does, it will be relatively slow. So kinetics and thermodynamics are independent. We can have a reaction that is favorable or spontaneous. It's a reaction where products are favored, but there can be a significant difference in the speed of the reaction. Here, because our transition state is only a little bit higher energy than our reactant, we have a small activation energy, which means this will be a fast reaction. In B, our transition state is much higher energy than our reactant, giving us a much larger activation energy, which means the reaction is going to be slow. Next, let's look at C and D. So for C, we are starting out with our reactant here and our product here. And so this is the overall energy difference. This is our delta G. And so here we can see that our delta G is positive. Over here, we have our reactants up to our products, much higher in energy. And here we have a much larger delta G. But once again, the delta G is positive. So both of these reactions are non-spontaneous or unfavorable. And at equilibrium, there will be more reactants than products. At equilibrium, more reactants than products. But again, we have a difference in the kinetics of these two reactions. So here we are looking at this as our activation energy. This is the difference in energy between the reactant and the transition state. I know the book has it labeled here. I just always show it here, and so that's why I'm redrawing the same arrow. In D, we're going from our reactant to our transition state, and this blue arrow is the activation energy. So here, the difference in energy between our reactant and our transition state is relatively small, so this reaction is going to be relatively fast. In D, the difference in energy between the reactant and the transition state, this is a significant difference in energy, which means we have a large activation energy, which means this reaction will be relatively slow. So I want you to be aware, here we're just talking about single-step reactions, but we have many possibilities. We could have a reaction that is fast and favorable. We could have a reaction that is slow and favorable. We could have a reaction that is fast and unfavorable, or a reaction that is slow and unfavorable. Combine these when we have multi-step reactions, and the overall thermodynamics, the overall kinetics becomes more complex, but we need to be able to pick apart the details so that we can understand how quickly a reaction proceeds, why it proceeds that quickly, and so that we can understand the details of the equilibrium as well. Now, once again, let's build an energy diagram for a multi-step reaction. So here we are starting with the reaction we've talked about before, ethylene with HBr, and this is the energy diagram for the first step. These are the reactants, and this is the carbocation intermediate along with the bromide. So here's our intermediates. This is much higher energy because our carbocation is unstable. And here we have the delta G of this reaction step. This would be the activation energy, or the delta G double dagger, so the difference in energy between the reactants and the transition state. If we look at our second step, then here we have our carbocation intermediate, and then here we have our product. And there will again be some increase in energy to get to a transition state, which will then come down to the product. So here is our transition state. This will be the delta G of this reaction step, and this would be the delta G double dagger, or the activation energy for this step. Now, if you choose to show multiple steps from the same reaction on separate energy diagrams, then you need to make sure you're being clear about whether you're talking about the same scale. Alternatively, and probably a lot better, is that you combine these together on the same energy diagram so that it is crystal clear that you are showing everything on the same energy scale. So here we have the reactants of step 1 going to the product of step 1, and then the reactant of step 2 going to the product of step 2. So reactant, transition state, product of step 1. So all the way from the reactant of step 1 to the product of step 1, this whole thing is step 1. And then here we have step 2. This is the reactant of step 2, the transition state of step 2, and the product of step 2. So this is the activation energy for step 1, and this is the activation energy for step 2. We can see that the activation energy for step 1 is much larger than the activation energy for step 2. So this tells us that step 1 is the rate determining step. So how quickly this reaction proceeds, how slowly this one proceeds, really doesn't matter, because the overall rate of the reaction will be determined by this activation energy. So the kinetics, the rate of the reaction, are determined by this step. The thermodynamics, the favorability, is determined by this energy difference between the overall reactant and the overall product. And then finally, once again, let's look at the same multi-step reaction we've been looking at, as well as a different multi-step reaction. So this is the reactant of step 1. This is the transition state of step 1. This is the product of step 1. This is the reactant of step 2, the transition state of step 2, and the product of step 2. This is our overall reactant and our overall product. And so here we have an intermediate. The thermodynamics are determined by the difference in energy between the overall reactant and the overall product. So this is what we're looking at here. For this particular reaction, we have a negative delta G, and so this reaction is spontaneous or favorable. And in terms of kinetics, this is the activation energy for step 2. This is the activation energy for step 1. Because the activation energy for step 1 is much larger, then step 1 is the rate determining step. And so step 1 determines the rate of the overall reaction. Now over here we have a completely different reaction, and this one happens in 3 steps. So this is our reactant of step 1, and this is our transition state of step 1 and our product of step 1. So we're going through the transition state to the product. And then this goes through the second transition state to the product of the second step, through the third transition state to the product of the third step. So reactant 1 to product 1, reactant 2, transition state 2, product 2, reactant of step 3, transition state 3, and product 3. So this is step 1, this is step 2, and this is step 3. In terms of thermodynamics, step 1 is endergonic, step 2 is really endergonic, but step 3 is really exergonic. But the individual steps don't matter when it comes to thermodynamics. What we focus on is the overall energy difference. So let's pretend this is a straight line coming out from the overall reactant to the overall product. This is the delta G of the reaction. Delta G is negative, and so this reaction is exergonic. Focusing on kinetics, here we care about our transition states. So from reactant 1 to transition state 1, this is our activation energy. So this is our EA1. The reactant of step 2 to the transition state of step 2, this is the activation energy for step 2. And then the reactant of step 3 to the transition state of step 3, this is the activation energy for step 3. Now, comparing these activation energies, it looks like activation energy 1 is about the same as activation energy 3. Activation energy 2 is much larger. And so for this reaction, step 2 is the rate determining step. Now notice the transition state 3 is a little bit higher energy than transition state 2, but it's not the overall height that matters. It's the height of the transition state relative to the starting material or the reactant of that step. So this energy difference is what determines the rate of this step. And because this step is the rate determining step, then this energy difference determines the rate of the overall reaction. Now, I keep forgetting to label my intermediates. So I did label my intermediate over here. So the product of step 1, the reactant of step 2, there is one intermediate for the reaction on the left. For the reaction on the right, this is an intermediate, and this is an intermediate. So in a 3-step reaction, we have one transition state, then an intermediate, another transition state, and then another intermediate, another transition state, and then our final product. Now, throughout the year of organic chemistry, we are going to be drawing and using and reading and interpreting many energy diagrams in order to help us understand the reactions that we are learning. So this concludes what I wanted to talk about in terms of this introduction to energy diagrams, but it's really only the start of the way we're going to use these energy diagrams.